So, welcome back to the deep dive. I want you to picture something for a second. You are sitting in your driveway. You press a button. The engine hums to life.
Or it silently activates if you're driving electric.
Right, exactly. And you pull out onto the road. You turn on the radio. You check the GPS. Maybe you engage the cruise control. It feels like a machine, right? Like it feels like gears and pistons and mechanical linkages.
It certainly feels that way, yeah. I mean, we have over 100 years of muscle memory telling us that a car is a mechanical beast.
Exactly. But I've been reading through this white paper on Linux automotive technology all morning, and it has completely shattered that illusion for me. The text makes a very bold, almost provocative claim right out of the gate. It says the modern car is, it's no longer a vehicle in the traditional sense. It is a server on wheels.
It's a striking image, isn't it? But when you peel back the dashboard, it is literally true. We are witnessing a transition right now that is just as significant as the move from horses to the Model T. We are moving from hardware-defined vehicles to software-defined vehicles.
And that's the hook for today's deep dive. We aren't just talking about cars getting better stereos or bigger touchscreens. We are talking about a fundamental architectural shift. But reading this paper, I kept feeling this, I don't know, this tension. A tension? How so?
It's almost stressful to think about. Because on one hand, we as consumers, we've been trained by our smartphones, right?
Right.
We want speed. We want updates every week. We want an open ecosystem where I can just download whatever app I want.
Right. We expect our technology to be fluid. We want it constantly improving.
But on the other hand, and this is the stressful part, this is a 2-ton metal projectile moving at 70 miles per hour on a highway with my family inside. If my phone crashes, I'm annoyed. If my car crashes.
It is a life or death scenario.
Yeah.
And that is the core conflicts we are unpacking today. How do you reconcile the, move fast and break things culture of Silicon Valley with the move slow and break absolutely nothing culture of automotive safety?
Right, which are complete opposite. Exactly. So the mission of this deep dive is to understand how manufacturers are trying to turn cars into innovation platforms without compromising that non-negotiable need for safety. And surprisingly, why Linux is the unexpected backbone of that entire strategy.
Let's start with the context, because I think a lot of us, myself included, we don't realize how messy the current state of car manufacturing actually is. Part 1 of the paper discusses the evolution of the machine. It talks about a shift from distributed ECUs to high-performance computing. Can you break that down for us? What does the old way actually look like?
The old way, which, by the way, is still how a lot of cars are built today, is what I call the messy desk architecture.
The messy desk.
Yeah. Imagine a desk covered in dozens of cheap plastic calculators.
Okay, I'm picturing it. Just a pile of them?
Right. And each calculator does exactly one thing. One calculator controls your power windows, another one controls the windshield wipers, another one handles the fuel injection. These are electronic control units, or ECUs. In a modern luxury car, you might have over 100 of these little chips scattered all over the chassis.
That sounds, it sounds chaotic.
It is a total nightmare from an engineering standpoint. First off, it's heavy. You have to run physical wires to every single one of those chips. The wiring harness in a modern car is actually one of the heaviest components in the entire vehicle, right after the engine and the chassis.
Wow, really? Just the wiring?
Just the copper wiring. But the bigger problem is that these chips don't really talk to each other very well. There are like 100 people in a room who all speak different languages and are just shouting at the same time.
So if I want to build a feature where, let's say, the windows roll up automatically when the wipers detect rain.
In the old architecture, that is incredibly difficult.
Because they don't speak the same language.
Exactly. You have to physically bridge the wiper chip and the window chip. You might have to flash firmware onto 2 completely different devices from 2 different suppliers who don't even talk to each other. It's slow, it's expensive, and it just doesn't scale.
And the solution to that is high-performance computing, or HPC.
Exactly. You sweep all those cheap calculators off the desk and into the trash. You replace them with one massive, powerful supercomputer. Instead of a chip for the windows and a separate chip for the wipers, you have a central brain. The paper gives a great example of this, actually merging light control and temperature control into a single processor.
So the same brain deciding to turn on your high beams is also deciding to turn up the AC.
Yes. And because they share a brain, they can share data instantly. This centralization is what makes the software-defined vehicle, or SoDeV, possible. You stop building hardware features and you start building software features.
The source material actually categorizes this evolution into 5 levels. using the MECE principle. I've heard consultants use that term before, mutually exclusive and collectively exhaustive.
Yeah, it's a fancy consultant way of saying we covered everything without overlapping any of our categories.
Right.
It helps us see where we actually are in reality versus the marketing hype. So, levels 0 through 2 are what we have seen for the last few years. This is basic software enablement.
Like getting a map update.
Exactly. You get over-the-air updates for your GPS maps, maybe a few apps on the infotainment screen. It's nice, but it's not revolutionary.
It's essentially a hardware car with a modem attached.
Correct. Then you hit levels 3 and 4, which is platformization. The car acts as a unified system. But the holy grail, the end goal described in the white paper, is level 5, the innovation ecosystem.
And this is the part that really caught my attention from a business perspective. Because level 5 isn't just about the car itself, it's about the economy around the car.
It changes the fundamental nature of the product.
Yeah.
In the old world, you sell a car for $40,000.
Yeah.
As soon as it drives off the lot, it's a depreciating asset. It loses value every single day.
Right, the second the tires hit the street.
But at level 5, the car becomes a dynamic platform. Think of it like the iPhone. When Apple built the iPhone, they didn't invent Uber or Instagram or TikTok. They built a platform that allowed those innovations to exist.
So the car becomes a stage for third-party developers.
Exactly. And that unlocks monetization after the sale. You can sell performance upgrades, autonomous driving features, specialized entertainment packages, or even an office-on-wheels software suite 5 years after the car is originally built.
It turns the car from a one-time product sale into a 15-year subscription relationship.
Which is exactly why the operating system choice matters so much. If you want developers to build cool stuff for your car, you can't give them a clunky proprietary system that nobody understands. You need an ecosystem.
Which leads us perfectly into part 2 of the paper Why Open Source. Because the argument here is that you can't build this ecosystem alone in a basement somewhere.
No, you absolutely cannot. The scale is just too big now. The white paper cites a Harvard study that puts the value of open source software, or OSS, at $8.8 trillion globally.
That number is hard to even wrap your head around.
Mm.
That's twice the GDP of Germany.
It proves that open source isn't just some hobbyist thing anymore where people are just hacking code in their spare time on the weekends. It is the invisible backbone of the entire global economy. And in automotive, we are seeing a massive shift towards this. The paper uses Mercedes-Benz as a case study, and I found this part fascinating.
Yeah, they compared the new C-Class to the recent S-Class. Now, traditionally, the S-Class is the flagship, right? It's the big, expensive luxury limo with all the absolute newest tech.
Historically, yes. The S-Class was always where you introduced the future, but the data shows that the new C-Class, the smaller, more affordable sedan, uses 3 times the amount of open-source software compared to the older S-Class.
That is a huge jump. It really suggests that this isn't just experimental tech anymore, it's moving into mass production.
Exactly. It's becoming the standard. And the paper identifies 3 main pillars for why Linux specifically is winning this war.
Let's walk through those. Pillar number 1 is talent. Now, this seems obvious, but explain the island of niche experts problem that the paper mentions.
Okay, imagine you are a legacy automaker and you decide, I'm going to build my own operating system from scratch. I'll call it CarOS.
Okay, I have CarOS. It's mine.
Well, nobody learns CarOS in university. Nobody at Google or Amazon or Spotify knows how to code for CarOS. So you have to hire people and train them specifically for your weird custom system.
You create an island.
You do. And when those experts retire or leave for another company, you are stranded. You have no talent pool to draw from.
Whereas Linux?
Linux is the universal language of computing. There is a massive global pool of talent. If you use Linux, you can hire a developer from a gaming company, a cloud company, or a fintech company, and they can start working on your car immediately. You aren't competing for a tiny slice of niche engineers. You have access to the whole world.
That makes total sense. Pillar number 2 is reliability. Now, I have to play devil's advocate here for a second. When I hear open source, I hear anyone can edit the code. To a layman, that sounds, well, messy. How can that possibly be reliable enough for a safety-critical machine?
That is the most common misconception. Think of it more like scientific peer review. Because the code is open, thousands of eyes are looking at it constantly. Bugs are found and fixed almost instantly. Security holes are patched by the community before most proprietary companies even know they exist.
The paper mentions some pretty heavy hitters using it.
It does. Linux powers SpaceX rockets, it powers NASA aerospace missions, and critically, it powers 100%, literally every single one of the world's top 500 supercomputers.
That's a strong argument. If it's robust enough to land a rocket booster on a drone ship in the middle of the ocean, it's probably robust enough to run my navigation system.
That's the logic. It is battle-tested in the most extreme environments imaginable.
Pillar number 3 was no vendor lock-in. They use a gaming example here, the Steam Deck. I love this analogy because it's really about power dynamics.
It really is. So Valve released the Steam Deck, which is a handheld gaming PC. They could have just installed Windows on it. It would have been easier in the short term. But then they would be paying licensing fees to Microsoft for every unit sold. And more importantly, they would be stuck following Microsoft's roadmap forever.
Right, if Microsoft decided to change how Windows works, Valve would just have to deal with it.
Exactly. So instead, Valve used Linux. But they needed to run Windows games, so they used a compatibility layer called Proton. This allowed them to run all the popular games, but they retained control over the operating system and the actual hardware.
And car manufacturers want that same sovereignty.
They are desperate for it. They do not want to be locked into a supplier who dictates terms for the next 15 years. They want to own the platform. Linux gives them that control.
So we've established that Linux is powerful, it's cheap, and it's flexible, but, and here comes the tension again, we have to talk about safety. This is part 3 of the paper, the snow chain paradox.
This is where the rubber meets the road, or, as the paper vividly puts it, where the rubber meets the ice. The analogy they use is trying to install snow chains on a speeding Formula One race car.
I love that image. It's so chaotic. It's just
Wow.
sparks flying everywhere.
It captures the engineering conflict perfectly. On one side, you have the F1 car, which is Linux. It moves incredibly fast. The Linux kernel receives about 500 patches and security updates per year. It is constantly evolving, changing, improving.
And on the other side.
The snow chains. These are the safety standards, specifically ISO 26262. These standards are designed to be static. They require extreme rigor. To certify software as safe under these rules, you usually have to freeze the code, document every single line, prove it behaves exactly as expected under every condition, and then never touch it again.
So you have one force that says update every day and another force that says never change anything or people might die.
Precisely. And we need to make a very important distinction here that the paper highlights. We need to distinguish between quality and safety. People use these words interchangeably all the time, but in engineering, they mean very different things.
Let's unpack that. If I say a car has high quality, I assume it's safe.
Not necessarily. In this context, quality refers to processes like SPICE. It answers the question, did we build this correctly? It's about minimizing bugs, having good coding standards, and following a strict process.
Okay. And safety.
Safety, specifically functional safety, answers the question, what happens when it fails?
That's a crucial shift. Quality hopes it doesn't break. Safety assumes it will break.
Exactly. You can have high-quality software that is completely unsafe. Imagine a navigation system that is beautifully coded, never crashes, runs smooth as silk high quality. But if it gives you a wrong instruction that sends you driving the wrong way down a one-way street, it is unsafe.
Right. And conversely,
You can have safe software that is low quality. Imagine a braking controller that crashes every 10 minutes. It's annoying, it's buggy, low quality. But if every time it crashes, it triggers a mechanical backup that safely brings the car to a stop on the shoulder of the road, it is safe.
so the challenge is, how do we take Linux, this massive, constantly changing F1 car, and certify it to that level of rigor? The paper mentions some failed strategies.
The most common mistake manufacturers make is retrofitting. They take the standard Linux kernel and they try to force it through the safety certification process. They say, we will freeze the specific version of Linux and document every single line.
But the Linux kernel has millions of lines of code.
Exactly. It's a black box in terms of certification. It is simply too big to audit line by line. And even if you try, let's say you spent 5 years certifying Linux version 4.0, by the time you finish, the rest of the world is on Linux version 6.0.
You've created a private fork.
And that is a trap. Now you are stuck maintaining this old, obsolete version of Linux all by yourself. You don't get the new security patches from the global community. You don't get the new drivers for new hardware. You are right back on that island of niche experts.
So you can't certify the massive Linux kernel. It's too big and it moves too fast. So what is the actual solution? The paper says the answer is isolation.
Yes. If you can't make the tiger tame, you put it in a cage. You have to change the fundamental architecture. This leads us to part 4 of the paper, the architecture of isolation.
The goal here is freedom from interference.
That is the technical term. Ideally, you want to ensure that if your music player crashes, which is a non-critical app, it doesn't crash your brakes.
Which seems like a very reasonable request. I do not want my Spotify playlist to determine my stopping distance.
Exactly. To achieve this, the paper outlines 3 dimensions of isolation.
Let's go through them. First is spatial isolation.
Think of this as memory management. Imagine the car's computer memory is a giant parking lot.
Okay, I'm in the parking lot.
The Linux system is allowed to park in section A. The safety system is allowed to park in section Z. Spatial isolation uses hardware tools, specifically the memory management unit, or MMU, to act as the parking attendant.
A very strict parking
The
attendant.
strictest. If the Linux system tries to park a car in section Z, essentially trying to write data to the safety memory address, the MMU physically blocks it. It doesn't just politely ask it to stop, it triggers a hardware fault. It prevents the corruption before it ever happens.
So even if Linux goes completely rogue, it's trapped in its own box. It cannot corrupt the data in the safety box.
Correct. Second is temporal isolation. This is about time.
Time, like making sure things happen when they're supposed to.
Yes. A general-purpose OS like Linux is inherently greedy. It wants to use the CPU to index files, update apps, run background tasks, but safety functions like deciding to fire an airbag need the CPU right now.
Right, you can't have the airbag waiting in a queue behind a background map update.
Exactly. So they use tools like hypervisors and hardware schedulers. These are like supervisors with stopwatches. They guarantee that the high-priority safety apps get the CPU time they need, no matter what Linux is doing. It creates a VIP lane that Linux cannot touch.
And the third dimension is communication integrity.
This ensures that the messages being sent between these parts are real. If the braking system gets a signal saying stop, it needs to know that signal actually came from the pedal sensor, not from a glitch in the infotainment system or some hacker.
And they use encryption for this.
Yes, end-to-end protection and a root of trust. This usually involves a dedicated hardware module, like a hardware security module or HSM, that holds the encryption keys safely. It's like a notary public stamp on every single piece of critical data.
So by using these 3 types of isolation, you can run what they call mixed criticality systems.
That's the economic benefit right there. You can run your fancy, high-quality, but potentially buggy infotainment apps, the quality management stuff, on the exact same chip as your critical safety apps.
Which saves money because you don't need 2 separate computer chips. You maximize your hardware ROI.
Exactly. You get the best of both worlds.
Now, this is getting a bit abstract, so I want to bring in the analogy the source material uses. I honestly think this is the best part of the white paper. They describe this security architecture as a castle defense.
The Castle Connectivia. It is a brilliant narrative device to visualize how these abstract pieces fit together. It turns code into characters.
Let's set the stage for this. Act 1 is the foundation. Every castle needs walls.
Right. In our car, the gatekeeper is Secure Boot. When you turn the car on, before the operating system even loads, Secure Boot checks the digital signatures of the software. It asks, is this the software I expect? If the signature doesn't match, maybe a hacker tampered with it overnight, the gate stays closed. The system simply refuses to boot.
And the walls themselves.
The walls are the data defenses. The paper mentions tools like dmcrypt for encryption and dmverity for integrity. These make sure that the data sitting on the hard drive hasn't been messed with while the car was turned off.
Okay, Act 2 is the inner circle. This is where the characters come in. Who is inside the castle?
First, you have TXet.
TUXet, obviously a reference to Tux, the Linux penguin.
Yes. TXet represents the Linux operating system. She is incredibly capable. She's brilliant. She can play movies, navigate maps, connect to the cloud, run complex AI models. But she's complex. She talks a lot. She might make mistakes. She's the eccentric genius. You cannot trust her with your life.
So who watches her?
That's Lisa. Lisa is the captain of the guard. She represents the safety monitor. Lisa runs in a completely separate safe zone, that's spatial isolation we talked about. Her only job is to watch TXet.
And who are they protecting in this scenario?
Princess V2 Abzoria.
Great name.
She represents the safe app. She controls the car's critical functions, steering, braking, acceleration. Lisa's job is to ensure that no matter what TXet does, whether she trips, falls, or gets confused, she never accidentally hurts the princess.
I want to drill down on the interaction between Lisa and TUXet. The paper mentions window watchdogs. That sounds technical. What is actually happening there?
It is a keep-alive mechanism. Imagine Lisa is holding a stopwatch. She tells TUXet, you need to send me a signal that you are working correctly every 50 milliseconds.
Okay, a heartbeat.
But it's stricter than just a heartbeat. If TUXet sends the signal too late, Lisa knows the system is lagging or frozen. If she sends it too early, Lisa knows the system is racing or skipping steps. The signal must arrive precisely inside the window.
So Lisa's standing there constantly checking the time. Are you okay? Are you okay?
And if TUXet misses that window, Lisa assumes the absolute worst. She assumes the Linux system has crashed or been compromised. And because Lisa has higher privileges, remember she is the captain of the guard, she can immediately trigger a hardware reset or cut off the outputs.
Cut off the outputs. What does that mean practically?
It means she physically disconnects TUXet from the controls. For example, if Linux AI that's planning the route stops sending valid heartbeats, the safety monitor can disconnect the AI's command from the steering motor and engage a backup safe stop controller that just gently pulls the car over to the side of the road.
That is incredibly reassuring. It's like having a designated driver who never drinks, never sleeps, and is always ready to grab the wheel.
That is the perfect analogy.
And finally, Act 3 is the long war. Because the castle isn't safe forever.
No, it's not. Outside the walls, you have Black Hood, the hacker. He is constantly looking for new cracks in the wall. He evolves, new vulnerabilities are discovered every single day.
So you need a way to fix the walls.
Enter Patchett, the royal advisor. Patchett represents the over-the-air update mechanism. His job is to constantly apply mortar to the cracks over the 15-year life cycle of the castle. Without Patchett, the walls eventually crumble under Black Hood's attacks.
I really like that story. It makes the relationship between the hypervisor, the safety monitor, and the OS so much clearer. It's not just code, it's a system of checks and balances.
It's defense in depth. That's the industry term for it.
So we have the theory, we have the castle, but does this actually exist? Or is it just a nice idea on paper? Part 6 takes us to the real-world solution. The paper explicitly discusses a product called EB Corbo's Linux for safety applications.
This is a concrete example of this theory in action. It's a software product built on Ubuntu, which is very popular, but it's compliant with ASIL-B and SISL-2 safety standards.
And it's verified by TÜV Nord.
Which is a huge deal. TÜV is one of the most respected certification bodies in the entire world. Their stamp proves this isn't just marketing fluff, it's real.
How does it work specifically? Can we give an example of a feature using this?
Let's look at the telltales. These are the warning lights on your dashboard.
The check engine light.
The brake warning light. In the old days, these were physical light bulbs behind a piece of plastic.
Simple, reliable.
But in a modern digital cockpit, these are just pixels on a high-resolution LCD screen.
Right. And if that screen freezes?
If the screen freezes because the Linux rendering engine crashed, you legally and safely must still see that brake warning light. If your brakes fail, you need to know.
So how does EB Corbo's handle that?
It uses that safety monitor, Lisa, to watch the video output. It analyzes the stream of pixels going to the screen. If it detects that the fancy digital dashboard has frozen or isn't rendering the warning icon correctly, the safety monitor intervenes.
What does it do?
It can overlay a simple safe graphic on top of the frozen screen. It literally draws over the Linux failure. Or it might sound a loud, audible alarm. It ensures the driver is warned even if the infotainment system is completely dead.
Another concept mentioned here is EOC, safety element out of context. That sounds like legal jargon, but the paper implies it's a huge time saver.
It is essential for speed. Usually you certify a safety system in context, meaning this specific brake pedal and this specific Ford F-150 is safe. Out of context means this software module is safe, assuming you hook it up correctly, no matter what car it is in. Think of it like buying a certified climbing rope.
A climbing rope?
The rope manufacturer guarantees the rope won't break if you use it right. They don't need to know which mountain you're climbing. They certify the rope out of context, the mountain.
That makes sense. So EB Corbo's is the certified rope.
Exactly. The car manufacturer just needs to prove they tied the knot correctly. They don't have to retest the fibers of the rope. This cuts research and development time by up to 50%.
Moving on to part 7, the long game. We touched on this with Patchett and the Castle story, but let's go deeper. The life cycle of a car is very different from consumer electronics.
A phone you replace every 2 or 3 years. A car needs to last 15 years, and the software needs to be secure that whole time.
And updates are scary. We've all had a phone update that made things buggy. But if a car update fails...
The bricking risk. The paper emphasizes that updates must be extremely robust. If an update fails halfway through, maybe the car enters a tunnel and loses its cell signal, it cannot become a brick. It must automatically roll back to the previous working version. This rollback capability is non-negotiable in automotive.
And there is regulatory pressure now, too. It's not just about good customer service anymore.
Correct. UNR 155. This is a regulation that essentially makes cybersecurity a strict barrier to entry for the European Union market.
What does it actually mandate?
It says that if you cannot prove you have a cybersecurity management system and that you can handle these over-the-air updates securely, you cannot sell your car in Europe, period. It puts the feet of these automotive executives directly to the fire.
It shifts the business model from a one-time sale to a continuous relationship.
It turns the car into a service. Continuous updates build trust. If I know my car is getting safer and smarter every month, I'm going to stick with that brand.
Finally, Part 8, Strategy and the Shift Left. The paper ends with a decision matrix for executives, but the most interesting part for me was this concept of shift left. It sounds like a political slogan, but it's really about timelines.
It's a revolution in engineering workflow. Traditionally, software development was dependent on hardware. You had to design the chip, manufacture the chip, put it on a board, ship it to the office, and then the software guys could start coding.
Which means the software team is just waiting around for months.
Exactly. Shift left means moving the software development earlier in the timeline to the left on the Gantt chart. How do you do that without the physical chip?
The cloud.
Yes. Specifically, things like the AWS Marketplace. You can create a virtual target. This is a software simulation of the chip.
So you can run the car's brain on a server in Amazon's data center.
You can spin up 1,000 instances of it instantly. Every developer gets their own personal virtual car to test on. You can run automated tests driving millions of virtual miles overnight.
Before the physical chip even exists.
6 to 12 months before, that eliminates the hardware delay entirely. You can test how the Linux system handles edge cases. Snow, rain, sensor failures, all in the cloud. By the time the physical car is built, the software is already mature.
That explains the time-to-market advantage. It's not just about coding faster, it's about testing faster.
And fixing bugs earlier. Fixing a bug in the design phase costs pennies. Fixing a bug after the car is on the road costs millions in recalls.
The Toyota unintended acceleration issue comes to mind. That was a nightmare for them.
A classic example of why this rigor is needed.
So, wrapping this all up, we've gone from the messy desk to the server on wheels to the castle defense, and finally to the shift-left strategy.
It's a complete transformation of the industry. Linux wins here not just because it has cool features, but because it is future-ready. It connects the car to the global tech evolution rather than locking it into a single supplier's roadmap.
The paper ends with a very powerful quote. It says, "Our software moves the world."
It is now a literal reality.
So here's my final thought for you listening. We are moving toward a world where cars are open innovation platforms. What happens when the App Store model truly hits the highway? Are we ready for a world where your car's features change as often as your phone's apps? Will we see freemium braking features? Or customized horn sounds downloaded for 99 cents? Or maybe your car refuses to drive to a certain destination because the map provider doesn't have a contract with that business. It raises fascinating questions about ownership and control.
Indeed. When the software defines the vehicle, whoever controls the software controls the drive. It's a brave new world for the automotive industry.
It really is. Thanks for joining us on this deep dive into the brain of your future car.
Thank you. Drive safe.
See you next time.
And hey, check for updates.